We're going to look at a connection between the average energy of a system and its partition function. I was going to show this in class on Monday, February 25th, but that got canceled due to snow. It's also an exercise in the Schroeder book, it's 6.16, but I thought it's non-obvious enough that it's worth working through. So first we can just take a step back and remind ourselves what the average of any quantity is. And this has nothing to do with statistical mechanics, it's just a general property of averages, that if you have some quantity x that you're thinking of, its average value, which we can write as x with angle brackets or x with a bar over it. Anyway, its average value is the sum over all possible configurations of the value of x in that configuration times the probability of being in that configuration. And Schroeder has a nice example of this in the text. And right, there's nothing deep about it. It's just a general statement about what probabilities mean. So just as a kind of dull example of that, here's something you can work on. Suppose your friend has a six-sided die. You get $2 if the number that comes up when you roll it is divisible by 3, and you pay $1 otherwise. So supposing you did lots of rolls, what's the average amount per roll that you'll get? So pause the video right now and work on this and make sure you can do this one. So pause. Good. So I'm going to assume you're done pausing now, and let's quickly work through this one. So here we're thinking about the average gain we get from these dice rolls. And again, just as with everything, it's the sum over all possible configurations of how much you would gain in that particular configuration times the probability of being in that configuration. Here there's only two possibilities. It's divisible by 3 or it's not divisible by 3. So our gain is plus $2 if we come up with a number divisible by 3, and that has a probability of 1/3, because there's two numbers between 1 and 6 that are divisible by 3. And then our gain is negative $1 times the probability of coming up with a number not divisible by 3, which is 2/3. And so we have 2 times 1/3 minus 2/3, so our average expected gain is 0. Good, and if you didn't get that, pause again and work through that once more. Good, moving on. We can think about the average energy of any system. And again, just to remind you, we're thinking of a system like maybe an atom or something, and there's lots of different energy levels it could have. Write them out in a ladder diagram or something like this. And our system could be in this state with this energy, or this state with this energy, or this state, whatever. And again, because it's in contact with a thermal reservoir at equilibrium, it could be in any of these states, because it could exchange energy back and forth with the reservoir, but there's different probabilities associated with each state. And again, we want to consider the average energy, which again, just from the property of averages, is the sum over all possible configurations times the energy in that configuration times the probability, the sum over all configurations of the energy in that configuration times the probability of being in that configuration. So now we can put some physics into this and write that this average energy, well, we can put in the Boltzmann factor for what the probability of any given configuration is. So we can rewrite this as 1 over the partition function, times the sum over all configurations of the energy in that configuration times e to the minus energy of that configuration over K2, okay, making use of the Boltzmann factor. Now, just for convenience, I'm going to define this thing beta as 1 over KT, so I don't have to keep writing things in the denominator. This is a common abbreviation to use. So my average energy, I could then write as 1 over the partition function, sum over all configurations of the energy in that configuration, times the exponential of minus beta ES. Good. Okay, so that's fine, and it's not particularly interesting. Let me also write down again what the partition function is. The partition function, again, this just comes from normalizing a probability, but it's an extremely useful function. It's the sum over all configurations of that Boltzmann factor, so e to the minus beta, the energy of that configuration. Okay, now we notice something interesting, that this average energy has an e to the minus beta es in a sum. The partition function has a e to the minus beta es in a sum. The two differ really only by this energy of a state that comes in front. So this leads us to wonder, is there any way I could turn this into something that looks something like this? And you can stare at it for a little while. Feel free to pause if you want to, but anyway, you could stare at it for a little while and then realize that a derivative of this would bring down a factor of ES. So let's write down that derivative. So we have the partition function is the sum over all states of e to the minus beta times the energy of that state. So the derivative with respect to beta of the partition function is just the sum over all states of e to the minus beta es, because the derivative of an exponential is just itself, times the derivative of what is there in the argument of the exponential. So we get a minus es in front of each term. So that's the derivative of the partition function with respect to beta. And now, writing again just from the last page, but now without my typo from before, that the average energy is just 1 over z times the sum over all states of the energy of that state, e to the minus beta es. We see that these two things look extremely similar. The only difference between these two things is that I have a minus sign here and I have a 1 over z here. So what that's telling us, just staring at these two equations, is that the average energy is just minus 1 over the partition function times the derivative with respect to beta of the partition function. So that's pretty neat. In addition, we can also write, so the derivative with respect to beta of the natural log of the partition function is just 1 over the partition function, because the derivative of a natural log is 1 over that thing. 1 over the partition function times the derivative of the partition function with respect to beta, just by the chain rule. Therefore, we can also write that the average energy is just minus derivative with respect to beta of the natural log of the partition function. Okay. So now in both of these things, this one and this one, however we want to write it, we have a neat relationship that basically relates the average energy to the partition function, which ends up being quite useful because in situations where you can write down an expression for the partition function, it is then easy to evaluate that to get the average energy without actually going through the trouble of figuring out the sum over all states of energy times probability. Great. And we will end there.